Hi guys, welcome back. We are on our last lecture of the semester. This is something I like to call kind of like the culminating lecture of the semester, right? It's like the end, how we wrap it all up. And I know a lot of you are probably like bored or overhearing about climate change. And there's probably some of you that are learning a lot of new things in this class. So, because we have covered a lot of this already, I think throughout the whole semester, we've been talking broadly about climate change and different effects, right? This is a pretty short and sweet lecture. So this isn't everything on climate change, but I'm going to go over specific regions and just a little bit of examples here and there globally. So let's get into it. Before we look at specific examples of effects of climate change and what that looks like, whether it's man-made, anthropogenic, or natural instances or natural causes, it's important for us to really understand fundamentals of weather and climate. So we should have some understanding of past climates and the causes of past climate change in order for us to say and prove like, hey, you know what? There is a specific change in climate data. This is how we can prove it, right? Unfortunately, today, this is still a theory, or I mean, it's not widely accepted. There is still a lot of people questioning and saying that it's not true and it's highly politicized. And so I'll just, stop there, but you guys understand where I'm going with that. So when we look at past climate, that's important because now we are able to say, look, thousands of years ago, CO2 emissions or the amount of CO2 in the atmosphere was much greater or lower or whatever, right? We have to compare. So we call paleoclimatology, that is the study of past climate. So before really we can assess the possibility of climate change today, we should have some understanding of past climates and causes of past climate change, right? So it's important to understand how scientists gather climate data. So we're going to go quickly through 6 different ways that we look at information about past climate. First way is through dendrochronology, or simply put, by looking at tree rings. Now, when we were very little, we learned that if you cut a tree down and you count those rings within that tree, right, what does it tell us? The age of the tree, yes. But those tree rings can tell us much more. Now, we're not going to cut down a 1,000-year-old tree just to look at information from past climate. That kind of would be, it wouldn't make sense, right? So what is done is you drill a hole or you drill a core, you take out this core sample from that tree. And so these small cores can be taken out without harming the life of that tree. So different rings can tell us different things. So you're going to have some rings that are thicker, as you see here, right? Some rings that are thinner. Some rings, some years they may skip a ring growth. Some years they may double in growth. So that's going to tell us different things that were happening in the environment. Climate-wise, right? Trees that grow in temperate areas increase their trunk diameter by adding 1 concentric tree ring for each year of growth. So by counting the number of rings, the age of the tree can be determined. During years when growing conditions are favorable, tree rings tend to be wider in years that conditions are harsh. So whether that's a flood or a drought or whatever the case is, right? So it can tell us much more than that. And some trees are thousands and thousands of years old, like the bristlecone pines in Northern California and parts of Nevada. Those are endemic to Northern California, to those eastern Sierras, and they've been around. I mean, it's said that since when the pyramids were being built, that these trees were around. And they're still around and alive. And, you know, we will lose them because the place that they're found, that tree line, is getting higher and higher because of warming temperatures. So they are a great source of information the older the tree is. Oceanic sediments. This is another way we gather information from past climate. Oceanic floor sediments, they provide a record of the changing oxygen isotope ratio in seawater over periods of thousands of years. So scientists, they can determine when periods of glaciation took place. So what would that tell you? That it used to be much colder during that period, right? So you also have these common marine like microorganisms. They excrete shells or their exoskeletons, all that organic material and the remains of those organisms, of those little animals, right? They are built up layer on the ocean floor. And so when you look at these layers, you can determine when those periods of glaciation took place. And it's kind of the same idea. You would drill a whole core sample into the ocean and be able to test it. Coral reefs. This is another way that scientists look at what our ocean levels were like in the past, because coral reefs, they develop in shallow water. So if your coral reef is far away from the beach, but you know that coral reefs develop in shallow water, what does that tell you? Well, that tells you that your ocean levels used to be lower, right? That our sea levels are rising, our ocean waters are rising. That means that there's more water in the ocean. That means that there's less ice, right? Because we're not losing or gaining water. It's either held as ice or in the ocean. So coral reefs develop in shallow ocean water, and the relative height of these old reefs can help us determine past fluctuations in sea level. Ice cores. This is another great way. When you analyze these ice cores, it also gives us information about past climates. Drilling down into glaciers, for example, it holds a record of snowfall, and it can go back hundreds of thousands of years in some locations. So it's a very precise way that they do it, but they take these long cores of ice and they melt it, and within that ice is little trapped bubbles of atmosphere. So within those bubbles of atmosphere, those bubbles of air, if you will, when you melt it, you're able, I don't know how they do this, but you're able to see what the atmosphere consisted of. So maybe there was more CO2, maybe there was more methane, maybe there was less CO2, maybe there was more salt from the ocean, maybe there was more dust. And that dust, maybe it came from Australia's outback or the sands of the Egyptian desert. I don't know. All these different things are like held in this like picture perfect air bubble of the past. So I think that's really interesting. When we look at these ice cores, they provide really direct information about the composition of the atmosphere in the past. So that accumulation of snow year after year after year that's fallen and compacted and turned into this glacier, those air bubbles from the atmosphere stay frozen in ice. Isn't that wild, you guys? I think that is amazing. Pollen analysis. This is another way that we look at climate from the past. You have airborne pollen from trees and other vegetation. It's preserved in sediment layers on the bottom of lakes and bogs and really any type of wetland. So what does that pollen, what can it tell us about past climate? Well, if this lake, for instance, is in a desert environment or a dry environment, and you have pollen from a plant that requires lots and lots of moisture, lots of precipitation, then that means that long ago it used to be more precipitation to foster that type of plant growth. Does that make sense? Relic soils. That's another way. By studying ancient soils, scientists can test the soil and find information about climate from the past. So now let's look at different causes. We know specifically that we as humans, there are anthropogenic causes, right? We know that we are emitting too many fossil fuels. The rate of extinction for species is very, very high. And you cannot deny the fact that, yes, as humans, recently, we have really kind of pushed that throttle in terms of climate change. But also, as a scientist, it is important to also say, like, okay, there are natural causes of climate change. Okay, it is natural. Now, climate change deniers will hold on to this and say there's no way that man has that kind of power to change the climate. Okay, and they will hold on to these natural causes. So when we look at our causes of climate change, there's like a lot of variables, right, that influence patterns of temperature, because ultimately we're looking at how the sun warms the planet and is re-radiated back out, and how much of that solar radiation is trapped and how much of it is re-radiated back out into the atmosphere, right? We're ultimately looking at that energy budget. So that incoming solar radiation, also the albedo, how much is reflected, because that has a lot to do with how much energy we lose, correct? How much is trapped, that concentration of greenhouse gases, how much of that warmth of that heat energy is trapped within the lower portion of the atmosphere, right? And then the transfer of energy throughout oceanic and atmospheric circulation. So these are just an example. There are a number of mechanisms which are likely to have had a role in past climate change and that are happening as well today. So the following slides that we're going to go through are going to describe different or several different kinds of mechanisms of climate change. Okay, so first one is atmospheric aerosols. What are atmospheric aerosols? Well, those are the non-gaseous particles in the atmosphere, right? We know we have permanent gases, variable gases, but the non-gas particles in the atmosphere, we consider them aerosols. So those can be pollen, dust, wildfire ash, volcanic ash, meteor debris, salt from the ocean, smog, automotive emissions, all those little particulates, if you will, they're hanging out in the atmosphere, right? Hopefully you can see them there. Now, not all of them are natural and not all of them are man-made. This could be a car emission particulate. This could be a wildfire little ash, right? This could be salt from the ocean, whatever the case. So like volcanic eruptions, they can alter global temperatures because so much ash is emitted into the atmosphere. They will have kind of like this cooling effect. So there is evidence of a large volcanic eruption that cooled the earth. It kind of dimmed the planet. It's like a global dimming. We haven't lived through one, but it is a possibility, and there is evidence of that. So like a super volcano that erupts, like Yellowstone, the last time it erupted, there was ash found all the way in Florida. So that is enough ash in the atmosphere to alter global temperatures. Anthropogenic sulfates, black carbon, right? All these things are also man-made and they will alter climate. How? Well, the sun comes in, warms the planet, and wants to come back out, but those little aerosols trap it. Or, on the other hand, they re-radiate that sunlight, not letting it come in. So it could add to the warming and it could also add to cooling, okay? Here's a picture of a volcano. Fluctuations in solar output. So there is a link between like past climates and variations in the energy output of the sun. And we've been looking at that for a long time. So researchers have looked at connections between climate and sunspot activity, for example. So sunspots, we know that those dark little spots that appear on the surface of the sun, some scientists think that several past climate events like the Little Ice Age or periods of glaciation, they kind of correlate or correspond with a period of greatly reduced sunspot activity. So that has a lot to do on the output of solar energy or the solar output, right? Variations in Earth-Sun relations. We learned about this the very first few weeks of the semester. Eccentricity of orbit. What does that mean? So we know the Earth rotates around the sun, right? And in elliptical fashion, and then one day it'll change its course, and that will have a big impact on our climate, on our weather, on our seasons. Obliquity of rotational axis. So right now, the axis is tilted at 23.5 degrees, right? It's facing the North Star. Cool, it's all good. This will change. It might go to 24, it might go down to 22. So the North Pole will either be tilted more towards the sun or further away from the sun. Yes, that's going to impact our climate. Huge, big time, our seasons, everything. Is it going to happen overnight? Probably not. Are we going to be alive when that happens? Probably not. And then the polarity, of the axis is tilted towards the North Star, right? One day, the North Pole will be tilted towards the South Star, Vega. So the South Pole will be facing the sun during our winter. Maybe I shouldn't put it that way, but that is going to change our seasons. Are you guys following that? It's going to change our climate. It's going to change what we know now. Again, we probably will not see that shift. So here is a little bit about that. So the way that we rotate around the sun now is elliptical. It can change to a circular orbit, the shape of the Earth's orbit, or eccentricity. And here we go. Here is a fancy word for something that we already know. And that's what science likes to do. It just makes you sound fancier. And the reason I say that is just kind of to get you guys more comfortable, right? It's just other words you have to learn. 100,000 years, every 100,000 years, that orbit route, I don't even know how to say that word, will change, right? Is it route or is it route? I don't know, you choose. You know, English is my second language, so I still say route. I don't know, whatever, that doesn't matter. But every 100,000 years, that will change. The inclination of Earth's axis, or obliquity, right? Here we go. Here's another term. Varies in a cycle lasting 41,000 years. So right now we know it as 23.5, and then maybe it'll change to 24 or 22. The orientation of Earth's axis, every 25,800 years, it'll change. Okay, so that will have an impact on our planet. Yes, our climate is always changing. Our planet is dynamic. There's changes, but you cannot deny the fact that the fossil fuel industry, the emissions of fossil fuels, the burning of fossil fuels, the emissions, all that animal agriculture, everything that we are doing because of the amount of people, not enough resources, is definitely putting a dent into the planet and changing our climate. And here we go, greenhouse gas concentrations. If humans were not on Earth, there would still be greenhouse gases. And the greenhouse effect is not something negative, right? We need it. If it weren't for the greenhouse effect, we would freeze, right? We need that solar radiation to kind of be trapped within that lower portion of the atmosphere, right? So water vapor, carbon dioxide, methane, these all play important roles in the regulation of temperature in the troposphere. However, we as humans, we have enhanced the greenhouse effect, right? There is more re-emitted heat, more re-radiated heat, less heat is escaping into the atmosphere, into space. Why? Because there are more greenhouse gases now, not just natural greenhouse gases, but we are also adding to natural greenhouse gases, but man-made greenhouse gases and man-made aerosols, right? So all these things is increasing those gases and aerosols that keep our planet warm. The roles of the oceans, they're also very important. They do help in regulating temperature. Oceans absorb a great deal of CO2 from the atmosphere. They have absorbed about a third to a half of carbon that human activities release. Once in the ocean, marine plants and animals remove carbon from ocean water through photosynthesis. Large amounts of this CO2 in the form of methane hydrates are found in oceanic sediments. If these methane hydrates destabilize by high temperatures, the trapped methane is released into the atmosphere. So we know that permafrost contains trapped methane, but there's also trapped methane in these oceanic sediments. If our ocean waters get warmer, all this methane is going to be released into the atmosphere. What will that do? Well, methane is a powerful, powerful greenhouse gas, 23 times more potent than CO2. So all that methane that is released, it's going to increase the warming, increase the sea surface or ocean temperatures, release more methane into the atmosphere. So we have this positive feedback effect. Again, that when we talk about the tipping point, this is the tipping point, right? We know it's bad and it gets to that point where it's just like the tipping point. Do you guys understand what I'm saying? It's like a runway effect, right? You can't, we already know the causes, effects. We know it's pretty bad, but we still have yet to see how much worse, and hopefully we won't see, things will get. Does that make sense? Okay. The effects of global climate change. We've talked about this all semester long, right? You have melting ice, rising sea levels, loss of plankton. You have releasing of methane within permafrost and oceanic sediments. Okay, all these things. These are different types of evidence of current climate change. The IPCC or the IPCC, forgot what that Intergovernmental Panel on Climate Change. They are the most authoritative international body providing information about climate change to global leaders. Findings in IPCC's fifth assessment report include updates from recent research like evidence of melting ice, rising ocean temperatures, rising precipitation, wildfires, all these things, right? The IPCC projects a rise of 18 to 59 centimeters by 2100 or 2100 or much more. Sea level rise is due to the retreat of glacier lost, thawing ice at the South Pole. Melting ice has a positive feedback effect on heating. Water absorbs more heat. We talked about this, causing more ice to melt. And then also black ice. This is also a positive feedback effect because there is so much soot and what's another word for it? Soot, ash, all those things in the atmosphere. It falls on places that have this white ice that should be reflecting the sunlight. Instead, now you see these patches of dark black ice which absorb sunlight, which cause the melting of these glaciers to melt like race car speed. Does that make sense? So instead of a glacier melting normally or slowly or at its normal pace, because it has that soot on it, if you're following me, I hope you are, it melts even faster, if that makes sense. And I think I had you guys watch a video about this already, and it's probably linked down here. So here is Muir Glacier in Alaska. This is 1941 versus 2004, and 2004 is a long time ago already. So it'd be interesting to see what this glacier looks like. That looks like a long time, 60-ish years. That is not a long time. geologically speaking. Rising sea levels, different places that we see this. So not only do we have the melting of glaciers, we also have ocean that is expanding. So it's kind of like this two-pronged effect. Yes, glaciers are melting, adding more water into the ocean, sea levels are rising. But as global temperatures get warmer, so does the ocean, and when seawater heats up, it expands. Anything that is warm expands. As temperatures warm, oceans expand. Sea level rising is from melting ice and warming temperatures. That's important to understand, okay? Changes in precipitation. As climate change occurs, precipitation patterns change. In some areas, dry areas will be drier. Wet areas will be wetter. Heavier snow and rainstorm and flooding in other areas. Availability and quality of fresh water, we will start to see that if we're not already seeing that. Sea surface temperatures become warmer. So what does that mean? Hurricanes are even stronger. And I don't even have to ask you guys, is that happening? We know that is happening. More powerful storms. As the earth warms, more water evaporates, and this releases more energy into the atmosphere, causing more powerful storms. Effects of climate change on organisms. Sorry, why did I say that? So the population of zooplankton has dropped 80% currently along the California coast since 1951. That's a lot. Why is that important? Because it's the base, the building block, like the base of the entire food web in the ocean. Populations of plankton-eating fish and seabirds have declined as temperatures rise in waters around Antarctica. Similar decline in shrimp have been reported. Reduction in Adelie penguin populations because those shrimp are gone. So you see it's like this cascading effect, right? Some species have shifted their geographic ranges in response to global climate change. For example, we have the western butterfly. It's disappeared in southern parts of its range. Lots of species will become extinct. We talked about that. We took a whole chapter on species extinction. And that's especially seen in species who have a very narrow temperature requirement, right? So like also if an animal only eats one thing, like the giant panda, the only thing they ate is bamboo, and the only thing they eat is bamboo, sorry. So God forbid if, some type of fungus attacks the bamboo because temperatures are too warm and it can't fight it off, then those pandas are critically threatened and will become extinct. Coral reefs and all the organisms that rely on those coral reefs are impacted already, and that's because of ocean acidification. You also have temperature-related coral bleaching phenomenon, and that's when you have your ocean water temperatures, they kind of exceed this threshold, and the coral reefs go into shock literally, and they turn white. So it's called a bleaching effect. Some of them are able to kind of come back, and some of them are just a loss. Effects of climate change on human health. In 2010, there was a heat wave in Russia. You have the spreading of diseases like the Zika virus, for example, food and waterborne diseases, respiratory diseases. So this is all what we are already seeing, right? Effects on agriculture. You have inundated river deltas, which are some of the world's most rich and best agricultural lands. So those river deltas will disappear because of the rising sea level. You also have agricultural pests and disease that cause, agricultural pests and disease causing organisms proliferate. So you have more pests and more diseases. You have an increased frequency and duration of droughts, that's already happening, and less soil moisture. Climate change around the world, really quick. quickly, we're going to look at the United States, South America, Europe, Australia, and Russia. So here in United States, we are seeing an increase in wildfires. Yes, this year especially. And that is probably something I should add to this lecture. Rising sea levels. For example, in Miami Beach, sea levels are rising exponentially. And you are going to watch a movie with this chapter this week. And Leonardo DiCaprio will go and talk to the governor of Florida and talk about what they're doing to mitigate that ocean water. This picture here is just a regular day water coming in to Miami Beach, and they have invested $400 million into flood water mitigation. What that is just the ocean water coming in, because Miami Beach is not higher than sea level. It's like at or below sea level. No, at or maybe a little bit above, right? And you have water just coming in, so they are raising the streets. They are pumping out that water. So that's one example, and I'll have a couple of videos about this linked in your module. In South America, you have changes in agriculture. They're known for having that coffee belt, if you will. Great location to grow coffee, tropical weather, lots of precipitation right at those tropics. Because of changes in temperature, you're seeing a degradation in quality of the coffee bean. So now places that grow coffee will change. It's shifting. That's a huge impact economically to these countries, right? Think about how much is invested into these farmers, these private farmers, who invest their whole life into growing this crop, and now for that crop not to grow at the quality that they want it to, and just lose a whole year's worth of harvest, that's huge. Venezuela, Mexico, most of Latin America, and the economy will suffer because of that. Climate change in Europe. So you see at these latitudes, you see how every latitude is still experiencing effects of climate change, right? Some places will be able to bounce back from it, find another source of income, or change their economy, but some places will not, right? So in these higher latitudes, like for Europe, even Russia, Canada, Alaska, you have that melting of permafrost. So that is posing a big issue. You also have the Arctic Ocean, which is supposed to be frozen. So there's no going through it. You kind of have to wait during the summer. End of the summer is kind of when they can go through. They're saying now this is opening up earlier than ever before. So the melting is happening more than ever before. And here's some good news. You have Sweden, which is going to be completely fossil fuel free by 2050, guys. So I think that the United States as a world leader, right, should be the one kind of paving the way and setting that example, but we're not. So you have a lot of countries that are kind of going through these growing pains, right? You have India, you have a lot of countries in Africa that are shifting. Their economy maybe is getting better, things are getting better, but the next step for them would be using fossil fuels. And it's unfair for us as the United States to say, well, the poor of the world, now they should move to solar power, clean energy. And it's really unfair for us to expect everyone else to do that. Does that make sense? And we as the United States, we have not made that shift. We are a very fossil fuel addicted country, and we're building bigger. Our homes are bigger, we're driving bigger cars, we're using more energy to heat those huge homes, cool those huge homes. So we will see what happens in the future. But I think it's awesome that Sweden will go fossil fuel free by 2050. Why so long? Because they have to give their economy and everyone a chance to kind of make that shift, right? That doesn't happen overnight. So we'll see what happens. Let's see. And then you have places on Earth that are already going to disappear in our lifetime. So the island of Kiribati is right off of the coast. Well, not right off the coast, but close to Australia in the Pacific Ocean, South Pacific Ocean. And you have a lot of islands there, and some of them are already disappearing. So for instance, Kiribati is this little island chain archipelago collection here, if you will. You have about 33 different reef islands. A lot of them are already underwater. The president of Kiribati, he is already sending people to other places. So these are refugees of climate change because that place is underwater. Like Kiribati, Tonga is under threat, Fiji, all these places in Samoa as well will unfortunately and are watching their islands disappear. Tuvalu will disappear. So this is the world's most physically and economically vulnerable area to climate change. And we will see in our lifetime, and I hate to say it, but these islands will disappear because they will go underwater. So there's a lot of people that have moved over here. So you can call them climate change refugees. The presidents and leaders of these countries are preparing their people to move because there's nothing, you can do to stop this ocean water coming in. All right, you guys, so this is our last journal, and I want to say thank you for a wonderful semester. I always learned so much from you guys and your journal entries, your discussions, your project, your research papers. I have read every single one, and I am amazed by the amount of learning you guys are still able to do, even if we're separate, right? So this will be your journal entry. I will have it up on your module as a discussion, and take care, guys. And remember, if you need any type of recommendation, letters of recommendation, or anything at all, keep in touch with me, and have a great rest of 2020. I mean, how much worse can it get? Knock on wood, right? All right, guys, take care.